Aloha mai kākou. Aloha. Aloha. Okay, thank you for having me, and thank you all for coming out on a Friday night. I'll do my best to make sure it's worth your while. First, it's nice to see that we're in the shadows of Mauna Kea, right? And we have our Oli. Yeah. Still working on my Olelo Hawaii. It's a nice room to have a gathering. So I'm going to talk about soil and try and make it so you can feel it. Yeah? But let's begin first with kupuna. Yeah? Our kupuna give us the insights and knowledge to go forward, right? And so before I begin tonight, I have two kupuna who are actually from this very island. And they were instrumental in helping me see things. And so first, we have Eri Ka'anana, Miluli. It's a little ways from here, but not that far. We all know Miluli, yeah? Old fishing village down to the dry side, Ka'u. Yeah? It's a little remote. Uncle Eddie grew up there, probably born somewhere in the 20s. Manaleo, he spoke a Hawaiian of the days of old, not the Hawaiian that I learned at Manoa. Yeah? And so he traveled the world, but he carried his ancestors with him. And he was in World War II, and he was a merchant marine, and he went all over the world, and he came back to Hawaii, and he settled on Oahu, and he raised a family. And during the later parts of his life, he was a very important figure at Ka'ala Farms in Waianae. Waianae is a powerful place, yeah? You all know Waianae? Yeah? And so Uncle shared his knowledge about all things Hawaiian and the world and life and Olelo. And we learned much from him about kalo and uala and ways of planting and just how to, as we see in this Aloha Aina. That is a nice little sign. We are Aloha Aina, yeah? So I want to acknowledge Uncle Eddie, a Big Island kupuna. He passed on some years ago, but he's still with us. And so he shared much with us, and I was fortunate to be with him for quite a few years. This is Goro Uehara from Kohala, born and raised on sugarcane plantation, probably around the same time in the 20s. And his trajectory was a little bit different from Uncle Eddie's. Is he not Kanaka Maoria? A good, see, I'm getting some problems lately. Okinawa. He's an Okinawa, who are good farmers, huh? Who's been to Okinawa? It's much like Hawaii, actually, yeah? Anybody been to Okinawa? Good farmers. Huh? He was a soil mineralogist in Manoa. And he went all the way up to the very top summits of science. But he never left the humble roots of Kohala. So whenever he spoke to people as people, not standing up here and going on about smectite and isoelectric points and whatnot. And he was my kumu at Manu. And he too has passed on, but he's with us. So I want to acknowledge these two who passed much knowledge to us all. And now they're going to help us move forward. That's Pokai Bay. It's a nice place. There's still some nice places on Oahu. But you don't need to come. You can stay right here. Alright, we're going to spend a little time with soils. They're different one from the other, just like you and I are different. They share some similar properties. But we need to understand diversity. And in that diversity, there's richness. But if we don't understand what we have, we might not do the right thing. So we need to get a sense of what we have. And then the queen. If we take anything from this evening, it's that organic matter is queen. Especially in the wet tropics. We're in the tropics here. Is it wet here? My buddy here was telling me he lives up above Laupahoehoe. Already had 270 inches of rain. Oh, wow. That sounds like Waialeale to me. Yeah. So Hamakua is wet, and it appears it may be getting wetter. And are we surprised? Well, actually, if we take a look at the latest climate models, they indicate and predict that the wet sides of the islands will get wetter into the future. And on the other side, the yang of the yin is that the dry sides will get drier, right? So we're going into some tricky times, yeah? Okay, and then we have to have some sense of acidity, especially in wet, rainy places, because that's where you get acid soils. And then we'll spend a little bit of time about, well, what are we going to do about it? Yeah, but first we need some common language, yeah? So, this evening we'll do some science talk. We're gonna, because science is a common language. You can be from Czechoslovakia or Vanuatu, and cation exchange capacity, surface charge on clay, doesn't matter if you're in Vanuatu or in Hawaii or in Senegal, it's the same. See what I'm saying? So we're going to use science as our foundation. But before I begin, I imagine we're all gardeners here. Somehow we're connected to plants and soil. Maybe we don't know exactly what's there yet. I didn't know that until I was 30-something years old. But I grew up with a mother. My mother is an amazing gardener. She doesn't even say, she says, I just plant plants, Jonathan. She likes flowers and vegetables. And she has one rule: hard work. It's what it's been. She's almost 80. She was out preparing the garden for the winter. Unfortunately, she didn't see the light and she left Italy and moved to New Hampshire. Really? How can you do that? But anyway, she's in New Hampshire, and the winter is harsh. So you have to prepare your soil. And what is the key thing? Make sure you put organic matter out around your plants everywhere. Good. All right. You ready? So let's just begin with some very simple generalizations. Oh, I don't know why we have A horizons here. Don't worry about that. But you can go online and say, what is soil? And you're going to get this nice, simple, very clear diagram that tells us, well, soil on average is 45% mineral, yeah? And then the 5% organic matter, and then some proportion air and some proportion water. Makes sense, right? Makes sense, okay? Probably up at my friend's place for the last few months, it's been maybe 95% water and 5% air, right? But if it starts to dry out, it'll get, somewhere around this. Yeah, and we can see, here's the organic matter quite clearly. In this soil, we don't see it so clearly. It just looks like that. Is there organic? Well, there is a little bit more organic matter up here than down here. In this soil, you can see it a little bit here. This soil, you can see it pretty clearly, right? That dark color, that's the organic matter. Okay? The mineral component of soil is what? What is it? Is it rocks? Glass.
Soil or clay and
almost there. Sand, silt, and clay. Okay, right there. We consider soil is defined by these four components, and the mineral component is made up of sand, silt, and clay. There might be rocks there, but we don't consider that soil. Why? It's a rock. It's not soil, it's a rock. Okay? So the mineral component of soil is sand, silt, and clay. Okay? Can we see clay? Can we see it? Individual clay particles? Can we see them? No, why not? too small. In fact, you need a scanning electron microscope to see individual clays. It's tiny, tiny particles. But we can see aggregates of clay and sand and silt in granules. But that's a mixture. It's a mixture. It's not pure clay. Okay, good. All right. So there we go. There we have it. We'll see why it's important to maintain some amount of air in soil. Saturated soils, you know, they're good for kamo, right? But not good for papaya. Who grows papaya here? Yeah? Have you seen a papaya tree die after heavy rains that don't stop for days? Yeah, it's because their roots can't handle saturated soils at all. Okay. All right. Very informal, huh? If you have a question or you want to say, hey, Brad, that's not true. You open up, man. Okay. There you go. Who knows? Okay. Now, so, let's go back a minute. Let's go back a minute. These soils are clearly different. Clearly different. How do we know they're different? Color. Very clear. Kind of yellowish brown, maybe a little red, orange, kind of reddish, brown, very red, black. Yeah? Okay, so soils are different. And it depends where on the landscape they are and upon some factors. But that's important to notice that these soils can vary dramatically. Yeah? This actually is a soil from not too far from here. It's right up the road, Mealani. You guys know the Mealani Research Station? Sitar runs up there, right before you get to Waimea. This is a Maile soil. This is soil from Guam. The hills of southern Guam. Where do you think this soil is from? It's from good guess. Good guess. But actually it's from Lanai. Pineapple.
Where?
That's pineapple. Lanai. Red. Who's been to Lanai? Have you seen the red soils in Lanai? This soil is from Waimea. Lualuale. Each one is very different from the other. Very, very different. Why? How'd they get different? Alright, so quickly, it's nice to get a sense that soils vary because they might come from a different parent. What would be the parent, typical parent of soil? Rock. Okay? And here, in Hawaii, it would be lava. But the rock is named something here. Basalt, right? It's a basalt rock. But it came from cooling lava. Yeah? So, rocks, are all rocks equal? No, they're very different, right? So we have granite is a rock, and it will produce soils very different from rocks that come from basalt. Yeah? Granitic soils that come from granite are typically very sandy and very acid. Why are they very sandy? Well, granite is a rock that's pop. It doesn't break down easily. Chemically, it's very stable. A lot of quartz. Can't break it up into clay. So it just gets smaller and smaller pieces that become sand. Yeah? It's acid because it doesn't have the base forming components. Yeah? A lot of silica. Rich. Okay, so parent rocks make a difference. We have two main rock types here in the Hawaiian Islands that give rise to our soils. We have basalt, and we have another rock type. Not so common on the Big Island because it's a young island. This is a very young island. But on our older cousin islands, you find this rock. It's white. We have some down Kauai High. Close. It's not sandstone, it's limestone. Calcium carbonate from the coral reef, right? That has been exposed. Okay, so that's the second parent rock. And soils that form from limestone or calcium carbonate are going to be different from the soils that form from the basalt. Yeah? One thing is those soils that form from calcium carbonate or limestone tend to be near neutral to alkaline. They don't acidify easily. Why? Because calcium carbonate produces lime. So they're self-liming. Good. Age is important. How old is that landscape? Is it just forming? Or is it millions of years old? Very important. So we go across the Hawaiian Islands and we see there's a nice age gradient from the very, very young, newly formed to quite old. For Hawaiian Islands, quite old. Kauai, 5 million years old. Big Island, well, just forming, as you all know. But there's an age gradient right here on the Big Island. Right? How many volcanoes make up this island? 5, right? The oldest being Kohala. Right? And so in a minute we'll see a map and you'll see that there's a little bit more diversity of soil on Kohala Mountain than on Mauna Kea or Mauna Loa, certainly Kilauea, right? So age is important in diversifying soil. Climate is a very strong factor in forming soils, how soils form. And what key component of climate really drives soil formation? Water, rainfall. Okay? We're going to see in a minute how nicely this rainfall gradient, you can predict soil fertility by rainfall gradient. Okay? You can predict soil fertility based upon a rainfall gradient. I don't have the slide here, but let's explore that quite nicely because it's not far away. Who's been to Hawi? Hawi, yeah, just down. Right, not far away here. Yeah, maybe it's that way. I'm getting confused. Yeah, I always go left. I don't like going right. Yeah? Anyway, we have Kohala Mountain. Yeah, at the top, it's quite wet, really wet. What's up at the top of Kohala Mountain? Rain forest, dense rainforest. Yeah, and then you come down the slopes, and what happens? It gets progressively drier. But the parent rock is the same. It's the Pololu lava flow. 300,000 years ago, yeah, it produced this lava flow. So it's the same rock of the same age from the shoreline all the way to the summit of Kohala. It's the same slope. The topography is about the same. Yeah. The thing that's really changing is the amount of rainfall. Very high rain at the top, almost no rain at the bottom. It's a desert down Hamakua side, right down by the ocean. Do we have a lot of soil down by the ocean? No, why? Because there hasn't been enough water to weather the rock into clay. Yeah, so it's just kind of sitting there. There's little pukas of soil, but it's mostly rock. And then as you move up the gradient, increasingly more and more soil, deeper soils. Yeah? Why? Because there's enough rainfall over time to start weathering the rocks into minerals, clays. Yeah? And then you get up to the summit and it's mostly clay. Mostly clay. Yeah, you haven't dug in those soils yet, probably. Make sure you ask permission first, yeah? But anyway, it's mostly clay. And we go from very nutrient-rich young soil, not chronologically different, but young in terms of vigor, yeah? In the lowlands. But it's shallow, so we can't use that for agriculture. But there's a lot of nutrients there, calcium, potassium, magnesium, and the pH is kind of high because there's carbonates around and have the weather. And then you go up into the middle and it's weathered a little more, the pH goes down a little bit. And it's still loaded with nutrients because there's not enough rainfall to leach it heavily. And that's where our ancestors planted their big field systems. 26 square miles of Kohala field. You've heard of that, right? The Kohala fields. Why did they choose that area to plant their crops 500 years ago? They didn't have soil testing technology. They knew these are rich soils and there's enough rain to grow the sweet potato. You go a little bit higher up, and now you're in the forest, and rainfall now is at, 200 inches a year, or 150 inches a year, and it's leached everything out. And you're left with what? Inert aluminum and iron oxide. Has no nutrients to big plants. Acid, 4, pH of 4. And that's not, it's 10 kilometers. Across that 10-kilometer gradient, you go from almost no soil to this beautifully rich. There probably is no soil like that on the planet. My wife says I exaggerate. But I would say that would be the best soil in the Hawaiian Islands, right there, in the middle. And then you go,
What town are we talking about? What area?
oh, Hawi, Kohala.
Okay.
Yeah. What's the ranch, the rancher there? Huh? Yeah, Kahua. Honoholo Ranch, exactly. Right in that, where those beautiful green pastures are when the rains come. That's the rich soil. But you go a little bit higher up there, and it's acid, because the rain has leached out all the nutrients. Okay, I got off track a little bit. Nonetheless, rainfall, very important. Yeah? High rainfall areas, no matter where you are, tend to have soils that are leached. They've lost their nutrients, and they're acidic. Okay. Low rainfall areas haven't leached. They tend to accumulate nutrients, but that doesn't make them better necessarily, because they may be too shallow, or the pH may be too high, or they may have too much sodium, salt. Plants, very important in soil diversity. And landscape, terrain, drainage. Is water leaching through, or is it ponding? It will make a big difference on what soil type is forming. So, keep this in mind. We're going to keep coming back to it. Yeah, we have 5 key factors that make soils different one from the other. What kind of rock they came from? How old is that landscape? How much rainfall and temperature? Is it warm, cool? What kind of plants were there? We'll get to this in a minute. And the shape of the land, the terrain. And that really is drainage. Is it in depressions? Is it on very steep land? Is it in land that percolates, lets water run through? And so we take that knowledge, those 5 factors, and we can see that soils vary dramatically across the planet. I won't spend too much time here. This will help us with the next slide, because we can classify soils. We can give them names, and in that name, we understand certain key properties of the soil. Just like when we say a mammal, we know what mammals are, right? They have gestation periods. I'm not a good zoologist, but a mammal and an amphibian, we have a sense. A reptile, an insect. The same thing, we can give names to soils. And those names tell us something about that soil. Let me just spend a couple of minutes to make sure that we can get a sense for this. The colors, don't worry about the names. That's not that important. But my friend here did already knew that, there's andisols on Hawaii Island. Well, let's choose that soil. Andisol. Okay? And it comes from ando, meaning black, from Japan. We'll get to that. Let's go to Japan. You can see there are andisols in Japan. See those purples? Yeah? There aren't too many andisols in the world. Yeah, there aren't too many. I chose this one because we're going to get to it in a minute. Here are some andisols. Here are some andisols too. You see the purple here? And then here are some andisols. Yeah? And then up here are some andisols. Do we know anything about those landscapes? Can you tell me anything unique about Japan? Kamchatka, I think this is it. Something like that.
Ring of fire.
Pardon?
Ring of fire.
Ring of fire, which means volcanism. This is high volcanic activity. And we're quite knowledgeable about volcanism here. Yeah? Maybe too knowledgeable, too close for comfort. Yeah? A few months ago, our sister Pele was giving a show to us, and it was producing lava flow, but most importantly, there were explosions, yeah? And those explosions were ejecting what? Ash. And that ash gets blown in the wind, and it's fine, very fine, and it settles on the landscape, and it undergoes weathering. And ash weathers quickly. It goes from mineral to soil-like in decades or centuries, which is quick in soil formation. Whereas those lava flows, it takes 10,000 years for soil to form, or 20,000 years for soil to form. You see the time scale we're talking about here? So all of these volcanic areas, lots of ash was ejected into the atmosphere, settled on the landscape, and weathered into a unique type of soil that we call andesol. And we'll explain its characters in a little bit. But you can see that those andesols occur where? Where there is volcanic activity. Yeah. You see this green soil here? Yeah, and it's here and here. Yeah, and we call it mollisol. Mollis, if I grew up in Europe and we had to learn Latin. I don't remember much Latin, but I remember mollis means soft. Yeah? So mollisol, soft soil. What do we know about these parts of the world?
Steppe prairie.
Green. It's green. Why did they give it green? What would
Rain.
Rain? Well, there is moisture here, but it's not super wet, actually. It's not. Nope. Grasslands. Exactly. These are grasslands, yeah? Here are the steppes. Here are the pampas. Here are the prairies. They're not prairies much anymore. They're soybean and corn. Yeah? But for millennia, millions maybe of years, these were the great grasslands of the planet, yeah? And those grasses have what kind of root systems? Deep and dense. And that root system combined with leaf litter fall built up organic rich soils. They're mineral soils, but they're rich in organic matter from all of that accumulated organic matter. And because they're not in a really high rainfall zone, the nutrients in those soils haven't leached out. They remain in the surface layers. These are some of the most fertile soils of the world. We know that the breadbasket of the United States, the most intensive agriculture in the United States is in the prairie states. Why? Well, because those soils were first and foremost inherently fertile. Inherently fertile. So why did they gain that fertility? It was primarily the combination of just enough rain to promote good grass growth, but not so much rain that you leach out nutrients, combined with grass that forms these deep organic soils. We were just on a statewide soil health survey, and we were up in Hamakua Ranch. Folks are familiar with Hamakua Ranch, and it was like an orgy of soil. The soils of those grasslands, the Kula grasslands, dark, brown, almost black, beautiful soils, loaded with what? Earthworms. Loaded. I felt kind of bad because we're taking soil sample and I'm cutting up earthworms. There's plenty there. Grasslands produce fertile soils. Here in Hawaii, where are great grasslands? Even before Poe came, before the Hawaiians came and made wala, and before we brought cattle and made ranches, what were those lands? They were kula. You know what kula means in Hawaiian? Open land. So grass and maybe some trees, savanna. Rich soils. Why are they rich? Just enough rain to promote vigorous plant growth and
The grasses.
grasses depositing tons and tons of organic matter that builds up there. And the lack of heavy rain, or meaning non-leaching environment, means the nutrients remain in the soil profile. Okay? And they tend to have a clay that is also fertile that way. Last one I want to focus on is these red soils. Yeah? I was born right here. Not quite in the red soil. What country am I in here? Colombia. Who's been to Colombia? Nice. I was just there. I went back and visited my cousin. Where were you born? I was born in Bogota, but I went to Medellin. That's the place I'm from. That's where my heart is. Yeah? Beautiful. Medellin has soils very similar to the soils here in Hamakua. Volcanic area, yeah? Volcanic. So, but you see these red soils here? Well, what's common? I was in Cameroon 2 years, a Peace Corps volunteer. If we were to fall out of an airplane and land in Cameroon right here, what would we see all around us? Desert? No. Wet jungle. Who said wet jungle? Yes. Dense rainforest. What's the temperature? Hot. I like hot places. Don't keep me away from the cold. Yeah. Hot and wet rainforest. Lots of rain. Hot and wet Amazon. Right? Okay? Now, oxysol. Oxys stands for oxide. Weathering. They're red soils in the subsoil. Totally red, like our soils from Lanai or Kauai. Weathered. All of the nutrients have been leached out because of the high weathering intensity. And we're left with iron and aluminum oxides. Yeah? Not fertile. Those parts of that soil is pretty infertile. But these soils produce huge forests. I've never seen trees like this before in my life. Dense forest. You go in the middle of the forest and it's middle of the day and it's dark like midnight. How can they produce so much growth if I just told you they're acid, leached, low in nutrients, iron oxides? The nutrients are in the plants. Good. But if they're all only in the plants, where are they going to get to keep growing new plants? So the plants are returning nutrients through litter fall, right? And that litter falls onto the surface of the soil. The microbes, the organisms shred it up and decompose it, and so you get that dark, black surface layer. Remember that first slide from Guam that I showed over here? Red in the subsoil, black in the surface. You have the organic matter in the surface that provides the fertility. That's the fertility of that soil. It's not in the minerals. The clays are infertile. So what happens if you clear the forest? Very quickly, you either lose the topsoil because the rain comes and washes it away, or if you're planting crops there, you use up that organic layer, and if you don't add anything back, you go from productive to non-productive very quickly, with a matter of years. 3 years, 4 years. So as a Peace Corps volunteer in Cameroon, the villagers I lived with, we'd go out and clear little parts of the forest to plant peanuts, plantain, and you clear a little bit, burn, plant, and you harvest the food from that cropland for maybe 2 years, 3 years, plant a couple more times maybe, and then pump, done, let it rest, go somewhere else. And they've been doing that for how long? Millennia. And it was working until what started happening? Population growth. Too many people, now they don't have enough place to go and switch. They got to keep coming back to the same place. Is one reason, right? Other reasons is deforestation, cutting trees for lumber to sell to Europeans so they can live in a nice house. Okay, diversity of soil, important, very important, yeah? let's come closer to home. Okay, here's Big Island. You see the same names over there? Andisol, Mollisol. We recognize those names now, right? Okay. This gray color, there's no soil there. I mean, you see this here? There's no soil here. There's no soil here. There's no soil down here. How come? No soil here, no soil here. Rust is lava flow, right? Yeah. Come back and check in 300,000 years. Might find some soil, right? Hasn't developed yet, right? But clearly you can see that andisols are the dominant soil type on this island. Make sense? Yes, the ash. You know, Hamakua, 20,000 years ago, was an active volcano, quite active, maybe 70,000. I don't know exactly. Geologists, go to your next geology lecture and then you can correct me. Yeah? 70, 50,000 years ago, this mountain was spewing out a lot of what? Ash and lava flows. And that ash blanketed the landscape. And then, what's the climate like along this coastline? Hot and wet. Hot may be an exaggeration, warm at least, and wet. It depends the elevation. As you go up, it gets cooler, but it's wet. And it's been raining on the Hamakua coast for 100 years? Thousands of years, right? Rain. And so that rain is acting upon the ash and turning the ash into clay. Clay. And because it keeps raining, doesn't stop, what happens to nutrients? They leach. Yeah? They're leaching out. Yeah? 500 years ago, had we had the opportunity to visit Hawaii on the Hamakua coast, we would have found probably what dominating the landscape? What vegetation? Forest. That would have been a forest, a native forest. As you went up in elevation, more koa, yeah? But it would have been a forest. Yeah? And that forest was very productive. As we know, the native forests that haven't been disturbed are very productive forests. Big koa, big ohia. The soil itself, the mineral component of all of these soils from Hilo all the way to Waipio and beyond, we consider them infertile. The mineral component.
Even in a productive native forest, it would still be infertile.
The mineral. The mineral. Like those red oxysols from the forests of Central Africa, the fertility resides where in these soils? In the organic matter. That's the fertility. Yeah? That's the fertility of the soil. That's the natural fertility of the soil. So, undisturbed koa forests, Mauka, produce koa trees for thousands of years because they're able to cycle nutrients through litter fall and one other very important symbiosis, two symbioses actually. Might as well say them right now. Yeah? Two critical symbioses. You all understand symbiosis, right? Two organisms, different organisms in intimate contact or relationship whereby both benefit. Yeah? And for these forests, the two symbioses that we cannot forget are biological nitrogen fixation, which is a relationship of a soil bacteria. There are some others, but mostly bacteria, and legumes. Koa is a legume. And they take atmospheric nitrogen, gas, inert gas, and with the production of an enzyme called nitrogenase, they convert that gas into reactive nitrogen ammonia, which then becomes proteins and amino acids and nucleic acids. And then they're cycled to the soil when the leaves fall. And it's a continuous cycle. The other key symbiosis that 85% of terrestrial plants partake in is called mycorrhiza, right? Mycorrhiza, which is a fungus, soil fungus, that infects roots, The fungus has hyphal network that exploits the soil's volume, brings nutrients to the plant, scavenges them, and water, and in return, the plant gives those fungi what? Sugar, carbohydrates. And they're both happy. And those are the two key symbiotic relationships that fuel a natural ecosystem. But we come along, and we're in a hurry. Even my wife's ancestors, Po'e Hawaii, they had to be in a hurry too, because we got to feed the family. And so what do? We cultivate. Yeah? And in cultivating, we disrupt, we disturb. And those symbiotic relationships kind of fall apart, especially the fungal ones, because you're tilling. Remember, it's an intimate relationship of fungi infecting roots and those extending that root system. And you come along and you're tilling it all up. It's disturbed, yeah? Okay. And the soil. Ash soils. Wet area, infertile. What about the endosols of Waimea and Waikoloa and mid-elevation Kohala? They're endosols, but they're a little different. They're fertile endosols. Why are they fertile? Less rain. Same parent, same vegetation, same topography, less rain. Rainfall in Waimea, on average, I know we can't speak averages anymore. We've now gone into a whole different realm, yeah? But 50-year average for rainfall in Waimea town, 30 inches. 30 inches of rain. It's not that much rain, but it's enough to feed grasslands. And when the rains come, what happens to those grasslands? They green up so fast. Why do they green up so fast? Because there's so much nutrients in the soil. You just provide the water, boom, you got growth. Yeah? What's the rainfall in Hamakua? Right here. 50-year average. 120 inches, 110. Yeah. Maybe more this year. Might be more next year. Leached. Leached environment, non-leached environment. Rich in nutrients, depleted in nutrients, but as long as there's an organic matter layer from the vegetation, the forest especially, you have fertility. Okay? Is that clear? All right, good. That's the main thing I want to say about this map, because the remaining soils, these soils here, we've called them histosols. Yeah, most people say that's not soil, Jonathan. That's just rocks and ohia forest or a macadamia farm. Well, you guys know they're Puna, right? You go down there and can you dig around? No, you're hitting rocks all the time. So these are young lava flows, 3,000 years old, 4,000 years old. We call them soils because if you take out the rocks, you'll get a fine material. You sieve it and you'll get some fines. And it's mostly organic matter. There's no clay there. There's some sand, but no clay. There's no clay in these soils. Organic matter and sand. Why? Too young. Hey, we're learning something. Too young. Too young. Where's the organic matter coming from? From the plants. Right. You can imagine that you come to a lava flow for several decades, there's a little bit of plant growth, and then all of a sudden you get ohia establishing itself, and they create a kipuka, right? You know that kipuka? Little area, and then more plants feed on, more organic matter here because the ohia is dropping leaves, creating roots, and you start getting these little puka of soils, and they start expanding, and you get more plants. And then, soon enough, you got a lot of rain down here, right? Rain's like crazy down here. And you got forests, Hapuna fern, ohia. And so the soil here is rocks plus organic matter. That's what it is. It's mainly rocks. But we call it soil because there's fines there that support plant growth. Let's not worry about Kona today. Do we need to talk about Kona? Yeah, we're talking enough about Kona. Yeah, let's stick to our Aina here. Huh? So, Andy, so how are we doing?
I have a quick question.
Yeah.
You know, you talk a lot about leaching. Is that related at all to how well the soil drains? Like better drainage would leach harder, or 200s on any type of drainage is gonna leaching?
Now that's a very important question. So leaching is in soils that allow water to percolate. Okay? Our soils here in Hamakua have good structure. My friend here, he told me we had 273 inches of rain already in Laupahoa. Am I exaggerating? No. Okay. And then what was my question to him? I kind of knew the answer, but I got to ask the question. So I said, did you have floods? Did it drain well?
It drains good.
It drains. Yeah? And that's because these andisols, they may have low nutrient status, but they have clays that form aggregates that behave like sand. And they allow water to move through them very easily. So it's quite rare for flooding to occur. Yeah? On the other end of the spectrum, we don't have good examples on the Big Island because it's still too young. But if we go to Waianae, and if we get a rain where I live in Makaha, if it rains more than an inch in an hour, that's nothing for you. That's like, hey, what are you talking about? If it rains more than 1 inch in 1 hour, my land floods. Totally floods. Because the clay type that I have in my soil swells up and doesn't allow water to drain. So it floods. We have floods in Waianae all the time. But we have low rainfall. It's low rainfall. It's because of the clay type. That black clay I showed you, when it gets wet, it swells up and it won't let water penetrate. So it floods.
But it doesn't leach as hard?
Oh, it doesn't leach. Well, it can't when it's swelled up, and then it doesn't rain much in Waianae anyway. So fertility-wise, well, we beat you guys out every day. But I'd rather have your soil. Because I'd rather have leaching than flooding. I can grow crops in the leach soil because I just add organic matter, compost, fish meal. But when my yard floods, my papaya die, and I can't do anything about it. Okay, see that's a good question. All right. Let's not spend too much time here. The language doesn't do justice to this, but we have to choose words, unfortunately. I'm still struggling saying that Hamakua soils are infertile ash soils. That sounds terrible. Ole pono kia. Ole mai kaikaina. The land is rich in Hamakua. But I told you the clays are not rich. So we have to call them infertile ash. As opposed to Waimea, Kohala, and Mikohala. You see, these are fertile ash soils. They have the same parent, they're the same age, same topography. The big difference is leached, non-leached. Nutrients lost, nutrients remain. Yeah? Okay. But these soils are good soils. You see, so we don't take infertile and equate it to bad. Okay? I just don't have a good word for it. Leached soil, you could call it. But that doesn't, I don't know if that does it justice either. You see our language, we need to develop some new vocabulary. Okay, we talked about this before. I spent just a moment here. I want to highlight again, although this soil is from southern Guam, as I mentioned to you, southern Guam is the wet tropics. Southern Guam is the wet tropics. A lot of weathering. Rainfall is intense. The mineral component of the soils of southern Guam is iron oxide rich, low in nutrients because there is a lot of leaching. The fertility of those southern Guam soils resides in the black organic matter rich top layer, surface layer. This equates to Hamakua. Nutrients in the organic matter, no nutrients in the clay layer. Okay? And you can go out and dig into your soils and you'll see there will be a gradient. Dark surface layer, and then slowly you'll start getting into yellowish, reddish, quite nice colors actually. Yeah? But you'll notice that your roots are mostly in the organic matter rich area, because that's where the nutrients are. Okay? We focus on clay because of the mineral constituents. Clay is the most interesting. Yeah? Clay has high surface area, lots of surfaces. Because it has high surface area, it holds a lot of water. So that's a very important role that this clay layer plays, is it provides water.
I gotta ask you a question about that, Jonathan. I've been experimenting with my soil for years, and also the neighbors tell me, hey, there's a term for this particular type of clay, hydrophobic. Does not want to mix. How do you explain that?
Okay. Wow, we got to get a little details there. It's only hydrophobic if it's dried out. Yeah. So there's an important thing about these soils. They dry irreversibly. If they dry out, the clay of these Hamakua's ash soils, if they dry out, you can't re-wet them.
But we're getting lots of rain all the time.
Yeah, but they don't dry out. These soils never, not yet.
Except under your house.
Correct. Right. If you shelter them from the high rainfall and they dry out and you try re-wet them, they repel water. They repel water. Okay. But in their natural state, they can't dry out because it's raining. Yeah? Does that make sense? Does soil ever dry out in your house?
I don't. Well, it cracks apart. There's times when we've had the drought, you know.
Okay,
last few years.
right. And then when you try re-wet it, it wants to repel that water. Yeah?
Yeah.
Right. So, you know, these
It's
are
not super saturated then, huh?
well, you just got to go slowly.
Wait for the rain
Well, the
cycle
rains
to
will
change.
come back and they won't dry out to such a degree that they dry irreversibly. I'm talking about taking the soil into a laboratory and drying it out and then trying to re-wet it. Well, you know, organic matter is going to help you there. You know, a surfactant. I mean, it's quite rare. These soils don't dry out on a regular basis. It's not something that we encounter yet. Yeah. So I wouldn't call them in their natural state hydrophobic. Let me give an example. I sent a student, he wanted to come to the Big Island to collect some soils. We were doing some composting work and we wanted to work with these andesols. I said, okay, go to Hamakua and collect some soils and we'll do some whatever studies at our lab. So we came to Hamakua, he collected some soils, up and down the coastline, brought them back to the lab, and then I didn't hear from him for a while. I had asked him to do the moisture content. We need to know what are we starting on? What's the moisture content of the soil? And it's 2 weeks. And that's something we do in 2 days. So, hey, Brother James. He was from Mali. You guys know Mali, West Africa. So I spoke French. Hey, James, what's going on? And so I said, and I asked him, what's going on? Where's cool. I think I got a problem. So what's going on? I keep getting wacky numbers. Yeah. First lesson in andesols. Well, what numbers are you getting? Well, I measure the water content and I come up with 250% water by mass. And he's new to andesol, so he's like, I'm wrong. How can it be 250% water by mass? Yeah. Remember I said that clay has high surface area? The clays of these andesols have 800 meters squared per gram of surface area. 1 little gram, like a thimble, marble in your palm, has 800 meters squared of surface area, which is doing what? Holding water. And so if you do it on a mass basis, mass of water per mass of soil, you get these outrageous numbers. 200% water. Right? And I can guarantee you, we go to your house, are you in Hamakua or in Hamakua?
Yeah.
Yeah, we'll go and we'll take soil samples right now and it might be 300% your land. I'm not kidding. Okay, all right, good. Did that we kind of went off track again, yeah? But did we learn something? All right, very nice. Okay, clay. Now, small, high water holding capacity. Some clays can hold high nutrients. We're going to get to that in a minute. But some clays are poorly drained. Your clay here in Hamakua is well drained. My clay in Waianae is very poorly drained. Cool, yeah? Okay. Allophane. Who's heard of allophane? That's the clay mineral of the soils on these andesite. All of the purple area, the main clay is called allophane. There's also some immobylite and some ferrihydrate, but it's mainly allophane. And allophane is tubular in structure. This is magnified thousands of times. These are microscopic particles. Our eyes cannot see them, but we know their structure. They're tubular in shape, so they have outer surface and inner surface. And so all of these surfaces can do what? Hold on to water. That's why they have this tremendous surface area. Okay? So, allophane has high surface area, as much as 1,000 meters per gram, very high water holding capacity, and these surfaces have a charge. They're charged. They can be positive or negative. Now that's quite unusual because the clay surfaces in my yard can only have negative charge. Only. That's only it. And negative charge is what we want. We want a clay surface to have negative charge. Why? Pardon? Right, to attract nutrients, because most of the plant nutrients, a good number of them, are dissolved ions that have a positive charge. So if the surface has a negative charge and the nutrient has a positive charge, there's an attraction. And what happens? It doesn't leach. Well, these allophane minerals can have either positive or negative charge, depending on their pH. And it turns out actually that in these Hamakua soils, there's not only allophane, but there's another clay mineral called ferrihydrate. Yeah? That under typical conditions out there has only positive charge. That's subsoil. So if your subsoil clay only has positive charge on its surface, what happens when calcium comes along? It's repelled from that surface and it leaches even quicker. What happens to magnesium? It has positive charge, it leaches. What happens to potassium? It has positive charge, it leaches. There's the explanation for why those subsoils are so nutrient depleted. They carry substantial positive charge. And we can go up and down the coastline, even up into the forest that has never been touched by human hands, and we get into the subsoil and we'll measure positive charge. But the tree, that koa tree, is not looking for nutrients in the subsoil. It's getting water from the subsoil. It's getting its nutrients where? From the organic matter-rich surface. Turns out that organic matter, humic materials, humus, also has charge. It's also charged. What's the sign? Negative. Negative. Holds nutrients. Okay? Good enough? All right, let's spend some time with organic matter. How are we doing on time? What flies when you're having fun? I have no idea what time it is.
Okay.
Okay.
You said pH affects the charge, yeah?
Yeah.
So if you raise the pH, you can make it negative?
Yes.
But
The higher the pH, the more negative charge. The lower the pH, the more positive charge in those clay minerals.
so the swoosh is just dumping a bunch of calcium on it.
Yeah, but to line your subsoil, you're going to go broke.
Oh, okay, but
Phew. Because you're going to have to dig it in. You know, lime won't leach down. You got to mix it. And it will only react with the layer that you mixed it with.
It won't dissolve and go down.
No.
So when I apply a whole bunch of dolomite on the field,
You gotta till it in.
how do you?
You see, so that becomes problematic if you have a pasture. You're not gonna go till your pasture. So you see, now we have to start thinking about plant adaptability. We have grasses that are acid soil adaptable. You don't need to lime them. But to lime a subsoil is expensive. Very expensive. And we would not recommend that on a large scale because you'd have to till down 2 feet, 3 feet. Think of the fuel cost. Think of the disturbance. There are other ways to get charge into the subsoil. Organic matter. Because organic matter mineralizes, produces soluble carbon, soluble organic molecules that leach into the subsoil and coat those surfaces. And in coating those surfaces, you get negative charge. Yeah? So let's go to organic matter. We're going to spend some time with organic matter, okay? So in the surface comes from decaying plant residues, which my friend over here says originated in the plant biomass. It can be wood, it can be leaves, all manner of life that decays, contributes to building soil organic matter, right? It's the life of the soil, and as we see, almost in every challenge that we face in managing soils, the answer is almost always found in organic matter, some aspect of organic matter. Our ancestors, no matter which continent, always managed organic matter to produce food. Always, all of it. So it's central. And I started off by saying it is queen. Let's see some of the things that organic matter does to a soil. Well, organic matter, remember organic matter comes from what? Decaying plant material, right? And who's acting upon the plant material or the detritus to take it from a recognizable tissue into some dark mix of microbes. And microbes secrete chemicals that act as glues. Yeah? And those are glues. You can see it actually when you observe earthworms. Yeah? Earthworm casts, have you noticed how they're nice and granular? They have a clear structure to them. Yeah? That is because there are glues that glue the clays and the silts and the sands and other particles together into those nice granules. And we call that aggregate stability. So the soluble carbohydrates, starches, myriad of chemicals that microbes exude or excrete act as a glue to hold particles into nice, observable, granular structure. And we want granular structure in soil because those granules hold water, but they also allow water to move through them. So we reduce ponding. When we have ponding, we get erosion. When we get erosion, we lose soil, right? So I put it first because in my mind, the first and most critical role of organic matter is building soil structure. And when we go measure whether a farmer is doing good work, protecting his soil, the first measurement we do is aggregate stability. How well do those aggregates stay together in water? So we take a soil, put it in like a little screen, and then we have a little instrument that will move that screen up and down in water. We do that for 10 minutes. We know the initial weight, and then we measure the final weight. The more the soil remains on top of that screen, the more stable the aggregate, the better it drains water, the more resistant to erosion. So we can quantify that, yeah? And it's unbelievable when we go to a kula soil up in a haleakala pasture that has been in grassland for 100 years plus, and we go to a farm vegetable soil, same soil type, and we run this test, what do we find? A dramatic difference. The farmer who's been tilling, adding fertilizers, hasn't had time or money or the resources to add organic matter, the aggregate stability disappears. When the rains come, those soils flood and erode. Very important property. Our job is to help people do that. And that's so easy when you have a 25-acre vegetable farm. And your income depends on how much lettuce you harvest. So, got balance. So, at the same time that you build aggregates, it helps water infiltrate. You want water to infiltrate, because if it's not infiltrating, it's running off, and you're causing erosion. Very serious problem. Organic matter makes a soil light. That's a good property for all of us. Yeah? How's your back? You want to dig a heavy soil or a light soil? Always a light soil. For farmers, a light soil means what? Less fuel. Easier to till. You make a soil light by adding organic matter. These soils actually are quite unusual. What's the typical density of a global soil? If we take the average value of a surface soil and measure its bulk density, mass over volume, what would be a typical number, average across the globe? It would be about 1.2 or 1.3 grams per centimeter cubed. That would be the average. If you took soils from Africa and Kansas, God forbid you went to Kansas, and whatever, and you measured their bulk density, the average would come about 1.2 to 1.3. What's the average bulk density of Hamakua soils? Whether they were in sugarcane or forest, the average. If they were in sugarcane, they got a little bit more compacted, yeah? If they're in forest, they're nice and fluffy. So you go from forest soil, bulk density 0.2. From 1.3 global average to 0.2 grams. That's how many times? 6 times less or more. And if you go to the subsoil that maybe is compacted, it's not going to be more than 0.6. So inherently, I'm going to come to you, inherently, andisols are light soils. And that's a good property. We like that. It makes them easier to manage. Dry weight.
1 centimeter cubed.
So 1.3 grams per centimeter cubed. That's the volume.
Same area, but like half the weight, even in the subsoil.
Oh yes.
So it's so much lighter. and
Much
fluffier.
lighter. That's why we call these, we describe these soils as fluffy. Pardon?
Ash-based.
Yeah, and it's because there are 2 reasons. One, allophane is tubular. Yeah, so it's got a lot of pores there, a lot of pore space. And secondly, these soils have a huge amount of organic matter. 14% carbon by mass. You know what the global average of soil carbon is? If we take the average of soils across the world for carbon, it's probably less than 2%. Our soils, even the ones that were really mishandled by sugarcane, are still 9% organic carbon. The pristine forest might be 17% organic carbon. That's a lot. Yeah. I get excited. I'm getting excited. So they're light. We like light soils because that means there's a lot of air space in them. Do you think roots like light soils? Yeah, they can grow easy, right? Okay, good. At the same time that organic matter increases aggregate stability and water infiltration, organic matter holds a lot of water. Why? Because organic humic molecules have a tremendous surface area. So they can hold water but at the same time they can transmit water. That's the perfect combination of the two. And organic matter protects soil against erosion, primarily because of this problem, aggregation. Okay? So this is the physical nature, and there are others. Well, we could probably spend 3 hours on this one slide, but we gotta move. Organic matter improves chemical properties of soil. Well, organic matter is loaded with nutrients. By its very nature, it's got nitrogen, it's got phosphorus, it's got sulfur, it's got calcium, it's got magnesium. In fact, it has all of the essential plant nutrients. Makes sense, right? It's derived from plant and animal tissue, so those nutrients are conserved within the organic matter after decomposition. Right? So, organic matter supplies essential nutrients. We'll get to the process by which amino nitrogen or amino phosphorus becomes ionic or mineral, call it mineralization. Organic matter has negative charge. The organic matter molecules are charged, supercharged, we might say. They have a lot of charge. Yeah? And so, because they have a lot of negative charge, they hold on to cations. Calcium, magnesium, ammonium, potassium, zinc, iron. These are all positively charged ions. So they supply nutrients, and at the same time, they hold on to them. They'll give it to you, but they'll also hold it for you for later. It's like a savings account. Right? Organic matter detoxifies several things, but I put aluminum here first and foremost because aluminum is ubiquitous in clay minerals. Most of our clay minerals are made up of a lot of aluminum. And if that aluminum is in an acidic, if that clay exists in an acidic environment, the aluminum dissolves out into the soil solution as trivalent aluminum. And aluminum attacks roots. Most plants cannot handle soluble aluminum. There are a few. Blueberries, tea. Tea is a very aluminum tolerant plant. Azaleas. So you get the point. Pineapple. What kind of plants tolerate aluminum? Plants that can tolerate acid soils. Yeah. Yeah, I'm not getting younger. Detoxification of aluminum. That's very important because if you go up into the forest lands up here, in the Koa lands, and we take a pH measurement of the soil, no humans have been adding things up there. If we take a measurement of pH in that soil, it's typically quite acid. High rainfall, rains a lot, leaches out a lot. There's a lot of organic acids as part of the organic matter. So it would not be surprising in that Koa forest to measure pHs in the surface of 5, 4.7. In fact, we were up in Nature Conservancy land on Haleakala, similar rainfall regime as this, and the pH was like 3.8. But it was the most beautiful native forest you can imagine. Not one single invasive species. All manner of koa. Yeah? Why? How can those plants handle that high aluminum? And because the pH is low, there's a lot of aluminum. Organic matter, it eats up the aluminum. That's a really silly name. Chelation. You've heard that word? Who's a chemist in the room? Chelation is organic acids that form bonds with the aluminum and protect it from the root, or protect the root. Okay? So that's why another key role of aluminum, of organic matter. Detoxification of aluminum in acid soils. For several years I was traveling to Palau. You guys know where Palau is? Palau is a small island in the Western Pacific, I was also traveling to Pohnpei. They're still living a relatively traditional life, but things are changing like everywhere. And they see the dollar signs and they want to change. Yeah, that's okay, change is good, but we got to be careful. And they're wanting to grow vegetables, but their soil's are acid. So they were hauling sand from the beach, coral sand, hauling it up to their field. They ever carried a 5-gallon bucket full of sand? I bet you can't make it across the road. That's an example, but it's heavy, right? And we said, no, you can do this easier. Make some compost with your pig manure and just add compost. You'll detoxify aluminum because those acid soils were aluminum toxin. So we detoxify aluminum. Also, those are the real key points here. We could go on as well, but you can see that's pretty important, right? Nutrients, nutrient retention, detoxification, quite important. And lastly, it's the life of the soil. So organic matter is the food for the organisms that live in that soil. So if you're continuously replenishing your soil with leaves and wood and manures, like a forest does, you're feeding the organisms. Yeah? A healthy soil, you've probably heard this. 1 teaspoon of a healthy soil contains on average how many cells? Living cells? 1 billion. Yeah? 1 billion or more. In fact, they say 1 teaspoon of soil has more living organisms than the population of humans on the planet. And it's not an exaggeration. It's loaded with life. And that life is diverse. And the diversity means that it's resilient. So perturbations will kill some of the organisms, but there's so many that are performing the same function that the system continues to function. These microbes, psychonutrients, we've said that several times now, right? They're taking that detritus, converting it into plant-available nutrient forms. Yeah? Microbial diversity promotes pathogen suppression. There's competition in that soil now. They're all going after food, right? Some are eating others, right? There are certain fungi that are going against nematodes, and vice versa. Protozoa are eating bacteria. It's not all love and peace and the kind, yeah? So there's a balance, yeah? There's pathogenic microbes in all soils, but in a natural ecosystem, there's a balance, yeah? Okay, good. So we could continue. Yeah, this is the frontier of soil science, actually, is describing life in the soil, because now we have new tools. You know, 1 gram of soil, 1 billion bacteria, 200 million actinomycete. What's actinomycete? It's a whole class of microbes that are sort of half bacteria and half fungi. Who makes compost here? Yeah? Here's your workers. These are the guys that are really working in a compost pile. Yeah? They can withstand pretty high temperature. Yeah, they don't freak out when it gets to 140 degrees Fahrenheit. Put your hand in a good cooking compost pile, what happens to your fingers? They burn up. Yeah? Protozoa eat other bacteria. And in doing that, they secrete mineral nitrogen. It's like a nitrogen factory. Yeah? Nematode. We think of nematodes as bad. Well, there are pathogenic nematodes, but there's a whole class of beneficial nematodes. And in fact, some people suggest that if you want to get a good measure of the biological health of your soil, you measure the diversity of beneficial nematodes. One, you can see them, so it's a little bit easier. And if you have a lot of beneficial nematodes, nematodes sit a little bit higher on the trophic level. They're eating other guys below them. So if there's a healthy population of them, there must be a lot of food. Right? Which means there's a lot of other microbes around. Okay? The problem is if you want to count nematodes, you got to sit down with a microscope and count them. You want to do that for a living?
Nope.
No. So I have a colleague now we just hired. He's a microbiologist, and he's trying to develop rapid tests for beneficial nematodes. Extract the DNA, do a quick test. We've got so many grams or whatever of beneficial nematodes in the soil. Hey, that's a good indicator. Okay? All right, nice. Let's keep going. Mycorrhiza. We talked about why do we care about mycorrhiza? Well, what is it first? It's a fungus. Mycofungus, rhiza. Rhiza refers to root. Root. Fungus root. Yeah? And you can see, here's the fungus hyphae that have infected this root hair, and they've made the surface area of this root hair expand many times. So now, this root might only have been able to absorb this quantity of water and this quantity of phosphorus. Now, with the help of this mycorrhizal hyphofungus, it can absorb many times more molecules of phosphorus or zinc. Huh? What does the fungus get out of it? Sugar. Good. Decomposition. We've talked about it. We can mimic decomposition by building a good compost pile, and we can optimize decomposition. A forest soil material might decompose over months, maybe a year. Sometimes you go into a forest and you still see that big log there 5 years later, but it's starting to get softer, right? We can accelerate decomposition by creating the conditions to optimize microbial activity. Yeah? So we make compost piles. And as you know, when you make a compost pile, you have to pay attention to several things, like?
Turning it over.
Pardon?
Turning it over.
Okay, turning it is a good practice, but even before we get to turning, when we build that pile, we want to optimize conditions. Okay, you want to balance greens and browns, and in technical terms, you want to balance carbon and nitrogen, but that's fine. When I worked with Pohnpeian farmers, I didn't say carbon and nitrogen, I said green and brown. Green materials are nitrogen rich, brown materials are carbon rich. So we have to balance that, get a reasonable ratio, 30 parts carbon, 1 part nitrogen. Okay? What else?
Herbicide.
Herbicide?
Particle size.
Particle size. Yeah. So you want to make the particles small. You don't want a big log. Yeah. So you shred. Yeah. You shred things up. That gives more surface area for the microbes to attack. Okay. Particle size. What else?
Moisture.
Moisture. Well, how much?
Sponge.
Just about.
Just enough. Not too much, not too little. Just enough. And what's the just enough? It's about 60% moisture by weight. Well, that's hard to measure. Yeah? But if a compost pile is too wet, what happens? It gets anaerobic. There's no oxygen around. And oxygen fuels microbes. Yeah? So it can't be too wet. What if it's too dry? Nothing happens because the microbes need water. So that's a tricky one, actually. Once you get the secret to getting that, let me know. It takes time. It's an art almost, right? You perfect your strategy. Anything else we got to consider? So we had carbon to nitrogen ratio. We had particle size, shred up the browns, the wood pieces. We said moisture, manage your moisture, not too wet, not too dry. Anything else?
I would say volume to make the heat.
Volume. Yeah, you've got to have a critical mass. You know, you can't make a tiny little pile of, okay, bro, I did my job. No, it's got to be a little big, right? Okay, we say 4 feet by 4 feet, something like that, by 4 feet. That's a good starting point. When you go to a composting operation, they have long rows, right? And they start off maybe 6 to 8 feet tall. Yeah? Okay. How do you know a compost pile is doing its work?
It's hot.
It's hot. How hot?
Yeah.
Well, what's the ideal temperature for composting? What temperature means
140.
you're at the ideal, huh?
140?
Yeah, you know, at least that's the minimum, actually.
145 to 165 something.
There you go. At least 145 degrees Fahrenheit, up to 165. It could be a little bit higher, but you don't want it to get too hot because what? Yeah, the microbes start going, hey, it's too hot, so you've got to keep it in that temperature. Now, my friend in the back said that turning is also a part of composting. Yeah? Why do we turn? Aerate it.
Get the things on the outside and get the interiors.
Get things on the outside that haven't started decomposing to come in the inside, so mixing, right? So turning will accelerate. Do you have to turn a compost pile?
No.
No. But it will accelerate the process. What's the typical time frame for composting, thermophilic composting?
3-4 months.
Pardon?
3 months.
Yeah. Yeah, and if you're going 4 or 5 months, that's kind of long. Yeah? Sometimes you can do it 8 weeks. Depending if you get really good at it. Yeah? Okay, so that's why we put decomposition up here, because it occurs naturally. The microbes are doing it continuously. But we can use that model and create optimum conditions to make compost. Yeah? Who makes compost? Everybody. I don't anymore.
Cheap.
Yeah, I feel terrible every day about that. Okay, so how quickly do things decompose? How quickly do they go from their original form into, converted form into different humic substances and others? Well, sugars and starches and simple proteins are immediately used up by microbes. They go right into the microbial biomass to fuel reproduction, right? So they're not even really decomposed, they're just used, assimilated by the organisms. Larger proteins, they need to be broken up into smaller pieces. How does that happen? You get large proteins. They're too big for a bacterial cell to incorporate it, to get it inside. So what do bacteria do? They produce enzymes. The bacteria produces enzymes, and those enzymes cleave bonds. They cleave it up, and then into smaller amide groups, and now the organism can take it in. Yeah? Hemicellulose and cellulose are pretty big molecules. They're also broken down by enzymes. Yeah? Organisms make the enzyme, and those enzymes break up the molecules into simpler molecules like starches and sugars that can be assimilated. And then we get into things that take quite a while to decompose. Waxy leaves, waxes and fats, and especially lignin and phenolic compound. Lignin is really the building block of wood, yeah? So wood takes a while to decompose. But eventually it does, and it's because organisms produce enzymes that break up the molecule. Okay? So rapidly decomposed and utilized by microbes, slowly decomposed and utilized by microbes. That's why wood takes a long time to decompose in the forest. Okay. This is a concept, we won't get too scientific about it, but it's a really fundamentally important concept, especially if you're farming organically, meaning you've decided you don't want to use mineral nitrogen from a bag that came from Haberbosch, right? We want to use natural sources of nitrogen. Nitrogen occurs primarily as proteins and other molecules that are pretty large, and a plant can't directly assimilate those large organic nitrogen molecules. There are some smaller ones that plant can use, but primarily plants use 2 forms of nitrogen, and we call it mineral nitrogen. It's not there's no carbon here, right? So it's not organic. There's no carbon here. And the most commonly utilized nitrogen molecule in soil plant systems is nitrate. You've probably heard nitrate. And nitrate is the last step in the oxidation of organic matter. So bacteria work on proteins in leaves, in manure, in flesh. Bacteria work on it, and fungi too. And they convert that organic protein form in a two-step process to ammonium, which can be used by plants, and nitrate. But the favored pathway is to go from organic form to nitrate as long as there's oxygen in the soil. Okay? And most soils are aerated, so this is the process. Organic nitrogen proteins to nitrate. And it's pretty quick. Yeah, you can go pretty quickly. But it depends on what the material is. So, this graph just gives you 3 different potential nitrogen amendments. Organic. I want nitrogen for my lettuce crop and I want to get it from an organic source. What should I use? Well, very often the top choice is something like fish meal. Great source of nitrogen for plants. Why is fish meal a good source? Well, it has a very low carbon to nitrogen ratio for one. Little bit of carbon to feed microbes, lots of nitrogen to get converted into nitrate. Yeah? And so you put fish meal into a soil, mix it in, and then you take measurements over time in weeks, and you measure the amount of ammonium and nitrate that have come from protein. And you can see, you start off low, the soil itself had a little bit of ammonium and nitrate, and you go within a week, you're getting 50 milligrams of ammonium and nitrate per kilogram, which is about, for these Hamakua soils, is about 50 pounds of nitrate per acre. About. That's quite a bit actually. You wait 2 weeks, yeah, and now you're up at 150 pounds of N. You wait 6 weeks and you're at 300 pounds, and then it sort of levels off, right? Why? Because the remaining amount, you added 400. The actual, we added 400. The total amount of nitrogen we added, the fish meal, maximum amount you got out at the end of the day was 350 pounds of N per acre. That's a heck of a lot, actually. Yeah. The remaining couldn't break down big molecules in this kind of meal. So what do we call this? We call this an excellent nitrogen fertilizer. Organic. Yeah. Fish meal. What are other good organic nitrogen sources that might behave like fish meal? Meaning they give the soil a lot of mineral and quickly, almost like a synthetic fertilizer. Chicken manure? Chicken manure probably is going to be down here somewhere.
With the spot that we got for fishing, you couldn't worry about farming.
That's an important thing. So you got to be careful because if you add this and you've got young plants and you're producing all of this ammonium and nitrate, it can cause some problems. Yeah? So you got to get the dose. But first, let's get the release curve. Yeah, let's get the release curve.
Wow, I'm really surprised at kukui nut being so high. It's
Wow,
hard to get
guys,
to
that
the
was-
sun here.
So kukui nut, this is the meal.
That's a good
They've
stuff.
taken the kukui nut and they've squeezed it to get an oil, right? We sell the tourists the oil, and we say, give us the meal.
Ah,
We want to grow plants. And I can assure you, my wife's ancestors, 500 years ago, were using kukui nut meal to fertilize. I can almost assure you. You go and look at all the ancient lo'i, and what tree will you find? Almost all around lo'i, kukui. Very closely tied to lo'i. And it's a good source of nitrogen. The problem is it's kind of labor intensive, huh? You guys gonna go out and pick a kukui nut and then sit there and squeeze it? It's too much work, huh? But if you hook up with a company that's making the oil that's giving to the tourists, you say, I'll take all your kukui nut meal. You can use it as fertilizer. It turns out, you've heard of copra? Copra? Now you take coconut and you squeeze it, get the oils, and then you get this meal left. Yeah? And it too is like that kukuina meal. So when I worked in the Marshall Islands, where they have a copra industry, they were throwing away the copra, the leftover meal. I said, nah, use it as a fertilizer. Why? Because it does this, it produces ammonium nitrate. Here's sun hemp leaves. It produces nitrogen, gives you mineral nitrogen, but much less than the fish meal. 10 minutes. See how quickly it goes? So you've got to choose which one you're going to use. High nitrogen organic fertilizers are things like blood meal, fish meal, feather meal. Those are the top. Intermediate, pig manure, chicken manure. Below that, cow manure. Cow manure and horse manure. Below that. Yeah? Goats would be low. You often look at the diet. What are the guys eating? Chickens eat a lot of feed chickens rich food. They produce rich manure. Guess who else produces good manure?
Humans.
You and I. We better start learning how to use it. Okay, good. 10 minutes, they said. I don't think I made it a quarter of the way through. Nature is funny though. Some materials will give nitrogen to the plant. Fish meal, chicken manure, blood meal, feather meal will produce abundant amount of nitrate to feed a plant. But some material, when you add it to soil, will feed the microbes, but not the plant. Because it has a lot of carbon and not much nitrogen. Okay, so you put wood chips in the soil and mix it up, the microbes go, hey, there's some carbon for it. And they start working on that carbon. But the wood chip has almost no nitrogen. The microbe needs nitrogen. So it says, oh, I better go look for nitrogen, and it gets it from where? The soil. And it takes that nitrate that was in the soil that a plant could use, and the microbe puts it in its cells. Who wins that battle? The plant or the microbe? The microbe always wins out when nitrogen is limited. The microbe, and we call that immobilization. So when you add dry brown leaves, coconut husk, sawdust, wood chips to your soil and mix it in, you essentially remove plant available nitrogen and put it in microbes, and your lettuce plants turn yellow.
Do you get the nitrogen back
Yes.
when they're completely decomposed?
Right. So that's the initial effect. You add the brown material, initially you lose plant available nitrogen, you go through a depression period, and then all of a sudden that brown is now being decomposed by the organisms and they start dying and other microbes are eating them, and you release nitrogen back to the soil. A year later, 8 months later, but you've lost your lettuce crop in the meantime. Yep. Okay. So we have the two things, yeah? We have giving and we have taking. So you can see that organic matter is feeding organisms, which is providing nutrients, giving it to plants, but you have to be careful what kind of material you're adding, because this pool could go into organisms and rob the plant, right? So you have to pay attention to that balance. Yeah? A note on nitrogen, we might end pretty soon here. I focus on nitrogen because for edible crops, vegetables, fruit trees, they like nitrogen. Taro, it likes nitrogen. And if you want a good crop, you don't want it to be nitrogen deficient. Yeah? It won't grow well. How do you know a plant is nitrogen deficient? It's turning yellow, especially the old leaves first, and then eventually the new leaves. Yeah? So you can see a plant is nitrogen deficient, it's turning yellow. And you got to do something. Okay? Remember, most nitrogen is in the atmosphere. But how does it get into biomass and microbes in soil? The first process, biological nitrogen fixation organisms. Nowadays we can make reactive nitrogen, Haber-Bosch, factory fertilizer. Yeah? Plant available nitrogen is nitrate and ammonium. The problem here, there's another conundrum. Nitrate, too much nitrate is no good. Why?
It leaches faster.
Pardon?
It'll leach faster.
Oh, it leaches quickly in most soils because there's negative charge around it, right? If there's organic matter, it's leaching out. Yeah? And where does it leach into?
The ocean.
Well, it can go into the ocean. Here, on the Big Island, it's mostly going to end up in the ocean because we don't really have aquifer system. We have some, but it's very porous, right? It gets into those lava tubes and it's gone. And when nitrate gets into the ocean, what does it do? It fuels algal growth. It smothers the reef. Now you get huge problems, yeah? Okay, that's an ecosystem damage. What are other potential damages for nitrate? Drinking water. If you have high nitrate in your drinking water and you have infants and you're feeding that infant nitrate-rich drinking water, they go blue. They asphyxiate. Yeah? It's kind of rare, but it happens in certain areas where you have a lot of nitrate in the drinking water. Okay? Okay, what else? Excess nitrate can also become nitrous oxide. If your soil is flooded, anaerobic, the nitrate turns into a gas and becomes a greenhouse gas. So you see, managing that nitrogen is quite important. And even if you're an organic farmer, if you're adding too much fish meal, you're getting excess nitrate. That excess nitrate is going to go somewhere. Either the atmosphere, the drinking water, the stream, the pond, the lake, the ocean. It doesn't matter where it came from. It's nitrate, yeah? So we got to manage that carefully. Are you going to turn me off? Am I turned off? Okay, I'll keep going.
3 more minutes.
3 more minutes. That's good because we'll make a discussion on pH. Quite an important, yeah? All right. So plants need nutrients. Nutrients must be dissolved. The elements must be dissolved. They must be nitrate, ammonium, calcium, ionic form. Yeah? Nutrients can be retained on clay surfaces and organic matter surfaces. We call that cation exchange or anion exchange capacity. But we really want it in the dissolved form. So pH in soil solution is a key driver determining whether the element is dissolved or in solid form. Very important driver. What is the pH of your soil? And we could, oh, this is the wrong one. I went the wrong way. Here's the next one. This graph is just trying to tell you where you have thick bars, that means it's in dissolved form. So we really see that in acid soils, we can have a nitrogen deficiency. It's mainly because bacteria don't like acid soils. So they won't nitrify. You won't get the mineral side of nitrogen. Okay? The real key ones to focus in on is phosphorus and these micronutrients because they're exceptionally sensitive to soil pH. Phosphorus, first of all, is poorly soluble. It doesn't like to be in solution. It likes to be a mineral. That's its preferred state. In acid conditions, below 6.5, phosphate reacts with iron and aluminum to form mineral. Variscite or strainite. These are minerals, so the plant can't get that phosphorus. So you see, if you have a soil that has a pH of 5.5, your phosphorus availability could be a problem. Could be a problem. Okay? That's a mineral precipitation. Phosphate with iron or aluminum. Okay? Mineral. At higher pH, above 7. As you go above 7, 7.5, phosphate reacts with calcium. In high pH soils, there's a lot of calcium. Calcium and phosphate react and you produce apatite. Bones, teeth, yeah? Not available for plants. So for mineral phosphorus, the ideal pH is around 6.5. That would be the ideal pH for phosphorus solubility. Now we're lucky. You see, because phosphorus can be organic forms too. Organic matter supplies phosphorus, and it's not as sensitive to pH. Not as sensitive to pH. That's why these forest soils produce phosphate, even though their pH is at 4 or 5, which is way down here, and you would predict almost no phosphate. The organic matter is mineralizing, the organisms are mineralizing organic phosphorus in DNA or chlorophyll or whatever, and turning it into phosphate, which feeds the plant. Yeah? At the high end of pH, not a problem typically in Hamakua. Our soils are not high pH soils. But you can make a mistake and add too much lime or too much rock phosphate. Yeah, organic farmers love to use rock phosphate. I got a call a couple of weeks ago. Yeah, I added 1,500 pounds of rock phosphate to my soil, and now my pH is 8.5. Yeah? So now what? You're up here, and you've got iron deficiency, manganese deficiency, zinc deficiency, because these elements react with hydroxides or carbonates and become solid. So pH you want to keep somewhere between 6 and 7. Okay? That's pretty clear. Yeah, there's where we went. And pay attention to pH because as the pH of the soil drops below 5.5, here are some of the potential problems. Calcium, magnesium, and potassium deficiency, or I should say common, in soils with pH of 5.5 or less. P deficiency, I mentioned it before, because at pH below 5.5 you have a lot of aluminum and iron which react with phosphate and you get deficiency. The real key is soils, as they go below pH 5.5, they solubilize aluminum and you get aluminum toxicity. But I told you there's a quite simple solution to aluminum toxicity, and that was add well-composted or manures are great to counter the effect of aluminum toxicity. Fish meal will counter the effect of aluminum toxicity. Okay, and then on Big Island, we're not old enough to have manganese toxicity, but on Molokai, parts of Maui, Lanai, especially Oahu, we have manganese toxicity in acid soils, not yet here. If in a little while, Kohala may start seeing some of that, but not quite yet. Okay? On the other end, we mentioned if you have pH above 7.5, phosphorus deficiency, micronutrient deficiency, and alkaline soils often tend to have salt problems. Typically not a problem in Hawaii, especially the Big Island. Typically not a problem because where we have enough soil to do agriculture, we have ample rainfall which removes salts, which leaches out carbonates, and so we don't get high pH. Okay? What are we doing, guys? As you can see, I could go on. We're 4 minutes over. It's up to you. I can do whatever you want. We can have some questions. The last thing I might cover, I just said that though a minute ago, would be liming. What do you do to an acid soil? You lime it? Let's do it real quick. Well, the first thing I would do, I'm not going to worry about this. The first thing I would do is add organic matter, because lime is expensive. Yeah, lime comes, you've got to buy it from somewhere. It's shipped over. So make some good compost, make some compost tea, get some fish meal, get some organic matter, add it to your soil, and you're going to counter the negative effects of acidity. First and foremost, aluminum toxicity. And all of those amendments add calcium, potassium, magnesium, phosphorus. So like my friend here said, if you have organic matter, don't go buy lime. Add organic matter. Okay? But you can add lime. You can buy local lime. They sell it down from Kauai High, crushed coral. They still sell it. Yep. It's not the best stuff. It's low quality lime, but it's local. If you want good quality lime, you got to import it from Saskatchewan, or I don't know where it comes from. Yeah. We said ideal pH is between 6 and 6.5. Why do we say that? Well, you're above 5.5, so you don't have to worry about aluminum toxicity. 6 to 6.5 is in the near optimum range for what solubility? Phosphorus solubility. And you're not too high to get micronutrient deficiency. Also, as we'll see in a minute, lime is expensive. Okay? So, you want to raise pH, it will do many things. It will increase phosphorus solubility, it will detoxify aluminum, and it increases the availability of these key nutrients because it helps bacteria. Bacteria like pHs between 6 and 7. They're most active. In very acid soils, they kind of go dormant, go to sleep. Yep. Okay. Also, you add lime because it's a good source of calcium and magnesium, dolomite. Yep. The most common lime material is calcium carbonate or crushed limestone. Calcium magnesium carbonate is dolomite. It's a high quality lime. It's a little more expensive, I believe. I'm not sure. But it's often a preferred liming material. In Hawaii, I don't think we need to go to dolomite. We have plenty of magnesium in our soils because the rock itself, basalt, is magnesium rich. Okay? So, but it's up to you. The key point of this slide is soils are like meat. They don't like to change. They resist change. So you can see in this graph, this is a hilo soil. There's a soil that covers many hundreds of acres outside of Hilo town. We call it the hilo soil. It's an andesol with a lot of ferrihydrite, and it's typically acid because rainfall around Hilo is high, lots of leaching. A hilo soil may start off with a pH of 5.5. You know, I would recommend doing something. If you have a pH of 5.5, do something. You're too close to the limit. Yeah? Okay, so let's say you start off at 5.5, and if you want to get to 6.5, you've got to add 4 tons of calcium carbonate per acre. 4 tons, that's 8,000 pounds per acre. Is that a lot? It is. It's going to cost quite a bit of money to do that. Do you need to go to 6.5? Not really. 6. Well, you see, if you add 1 ton, you get to about 6. Okay? So, remember, there's no real magical pH number. You've got to be at pH 7. No, that's a fallacy. You want it to be near 6 if you're down below 6. So, don't waste your money. So a ton, 2,000 pounds per acre, that's still quite a bit of lime. Now remember, I said before, you've got to till it in. If you just spread lime on the surface of your soil, the only place you'll get a pH change is in the top 2 centimeters of your soil. That's it. Even if it's rained 200 inches, the change, it doesn't leach into the soil. The liming effect when you use calcium carbonate is limited to the area depth to which you mixed it. So for tree crops, this becomes a little bit of a challenge because if you have subsoil acidity, you can't use lime as a remediation strategy because you can't till it in. Okay? So let's say you do have an orchard and you have what appears to be calcium deficiency or some pH related thing, you can use gypsum, calcium sulfate. It will leach down and give calcium at least down into your root zone. And you can combine that with compost and compost teas that are going to be leaching carbon molecules into the subsoil. Okay? But you can't spread lime on the surface and expect a change below the surface. Is that clear?
Is it better to dig a bigger puka when you plant the tree and put lime inside?
Okay, right. So if you're establishing an orchard, one approach, but it's a lot of work, as you can imagine. You dig a puka, you buy your lime or your organic matter or your mix of both, you mix that material, put it back in the puka, plant your tree.
But is it better to dig a bigger hole than?
Well, of course it would be better, but it's going to be more expensive. It's going to be labor and material-wise. If you can, I mean, yeah, to give a good start to your tree, that's yeah. I mean, you can't say the bigger the better because, my God, you know, reasonable.
Yeah.
Yeah. But that's a strategy. Okay, so lime can be expensive. Yeah, you can stop. Good enough, huh? There was no way we were going to pretend we were going to go through all of soil science in 2 hours.